Buenas tardes.
Buenas tardes, profesor.
Profe, buenas tardes.
¿Cómo están todos?
Uy, eso.
¿Cómo están todos? ¿Tienen alguna pregunta, alguna duda, consulta mientras esperamos? Esperamos un minuto más para empezar. Okay, so let's begin. Share my...
Profe, ¿le puedo hacer una preguntita rápido sobre una cosita del deber?
Ajá, seguro.
Sí, una cosita es del ejercicio 4. Solo quería saber si es que el potencial B es con L y M, los subíndices, o sea, si es con L y M, o está ahí un error de escritura o algo. No sé, es como que no quiero estar seguro.
Homework. Ejercicio 4.
Debía ser KL.
Ujú, eso es lo que yo
Sí,
digo,
sí.
debía ser KL, ¿no?
Sí, sí, por
Sí,
supuesto.
yo le había preguntado igual al profesor eso y me dijo que era con KL.
Sí.
Ah,
Y
ya,
aquí
Igual
están sumados,
en
¿no?
el último ejercicio. Sí.
sí, justamente yo también
Igual
hice
en,
con L, pero no sé, no estaba seguro si es que había un error o yo me equivoqué. Gracias.
sí. Igual en el último ejercicio también hay un error en la parte del argumento del seno. Falta multiplicar por n.
Falta un entero en el argumento del seno y del coseno. Falta el del argumento de seno en la expresión del eigenket. Falta una n también.
Mm.
Porque la k está cuantizada en unidades enteras. Esas son dos correcciones que van ahí.
Profe, otra pregunta. ¿El deber tenemos que mandarle al correo o lo subimos al módulo?
No, mándamelo al correo mejor.
Ya, listo.
Okay. Okay, so any other questions? Okay, so last time we were looking at the Hartree approximation. Okay, so this was the sort of the simplest approximation we could make. Turns out to be the one that was first devised by Hartree. And in terms of the Green's functions, it turns to take into account a diagram of this form. Okay? Remember, last class we did this diagram in KT space, and now here I just write it in K omega space. Okay, and then there was an intermediate momentum here. Okay, so the propagator expansion was simply to assume that this diagram, and we made a good argument. Okay, dominant diagram, and we reasoned this out in terms of the integral. Okay, so this we expanded in this way. Okay. And so on. Okay. So then we could apply Dyson's trick, which was to separate the propagator. So we get term 1, and then we got I'm going to put that arrow in the top so that the diagrams don't get ugly. Okay, and so on. Okay, and then we identified this term here, and then we have the square. Okay, square, a linear term. Okay, And then we could sum up those as we are. This is all algebraic, right? In K omega space. This is algebraic in K omega space. Okay, so we would get then 1 over 1 minus the diagram I have there. Okay, then we could divide by the propagator that's multiplying, okay? And then we got the inverse of this propagator minus just the Hartree contribution, okay? Let's put here, and then we remind you that this has an internal sum there, okay? So then we translated, okay? Any questions up to now? So this we did last class, we're just reviewing what we did. So we translate this, okay, Feynman rules. Okay, and we get that I, G plus K and omega, the full propagator, is going to be equal to 1 over I, G naught plus, okay, K and omega, to the minus 1, and then minus, okay, and translating this diagram, we have the fermion loop. This gives us a minus 1. Then we have to sum over the internal momenta, okay. Then we have the interaction line, which is I over 2, and then KL, in this case, KL, for the Hartree term, okay? And then we have a minus 1 due to the propagator at the same time propagator, okay? And that's it. Okay, so this is just the interaction line, the loop here, which is just, and so we get the minus sign here because of the same time Green's function, and then the fermion loop we get here, fermion loop. Okay, and this is equal time G naught. Okay, and then here we get the interaction here, just the interaction line, the little handles. Okay. Okay, so we get this this form here, and then we can simplify. Okay, and we get the final form. Okay, we know that G naught plus is just 1 over omega minus E sub k, and then because of the plus I get plus I delta. Okay, substitute it there, and we get finally this expression. So G plus K and omega is going to be equal to 1 over omega minus epsilon sub k, which is the free particle energies, and then we get the sum over L smaller than Kf, okay? V KL, okay, plus I delta. Okay, recall that we have these symmetries in the integral, so KL, if we switch the first two indices and the second two indices simultaneously, then, okay, this is exactly the same. The integral is invariant. This is just changing R, okay? This amounts to change R for R prime in the integral, okay? So the integral is invariant. Under that, it's changed. So these two matrix elements are the same. Okay, so this is the form that we get, okay? And from just inspection, okay, this is a simple pole. So this should be a particle, okay? It's called a quasi-particle, quasi-particle. And what's the energy of the quasi-particle? just identifying E prime of K is going to be just the energy associated with this frequency here, the new pole, okay? New pole is going to be at heaps of K plus L, okay? KL, KL. Okay, so we do that integral, the integral corresponding to this matrix element. Then I'm going to show you how to do the summation here, okay? And so we obtain the corrections that associated with the interaction onto the free particle energy. So we obtain the new quasi-particle energies, okay? Quasi-particle energies. Okay, so that would be it. There's another detail which is here. Recall that this integral here is not yielding any imaginary part, so that we can take delta to 0. Okay, so let me just make this comment here. Comment. So the correction to free particle energies yields no imaginary part. Okay, which implies that delta can be taken to 0, okay, because we know that this is just a regulatory parameter in order for the integrals to converge. So this means that 1 over tau, okay, is 0, so tau goes to infinity, so a quasi-particle lifetime, quasi-particle lifetime okay, is infinite, okay? So good. Any questions there? So this is the whole interpretation of the Hartree result, okay? This is the Hartree result, okay? Hartree result, okay? And this is the how we obtain the energies. Once we do the calculations, we just by inspection identify what the new energies are going to be, okay? Last class, we also did then a reinterpretation of the Hartree correction, okay? So let's change colors here. Interpretation. And this is very important for physicists. We just don't do the mathematics. Okay, but we need to understand what they mean, what it means. Okay. So we just wrote down the correction, which is K smaller than Kf, and then V of KL, okay? And this was the summation L smaller than Kf, okay? dr prime dr, and then phi of K. Okay, which is the form that we are going to use in the second quantized form of the two-body interaction, and then we get the two other. Okay, no conjugation there. Did I do here? Okay. I put some. Be able to eliminate this. Good. Okay, so we have this form, and what we do is that we rewrite this integral in the following way. So the r prime integral. Okay, so we write here the integral dr. Okay, and then we have phi k r. Okay, so we're going to notice that this has label L. So this is a label associated with the bubble, this L and this L. So we extract the K, which is associated with the particle that we are injecting into the system. Okay, then we put the summation here over L smaller than KF. So these are all the things that are going on with the hole that's being generated in the tadpole diagram. Okay, let me put here a parenthesis here, and then we integrate over dr prime, okay, which is the case for both sides of the potential here, and we make here this kind of an effective potential. Nobody noticed I missed a conjugation there. Okay, so r prime v r minus r prime phi prime. We close, and then we're left with the other wave function k unprimed, okay, unconjugated. Okay, so notice here that we could, this term here, okay, we can identify as an effective potential. Okay, and it has external variable r. Okay, so notice, and this is something you should, I already posted homework number 2, and this is something I asked you in homework number 2, so make a note of this. So notice that if I identify this as an effective potential, this turns into this following form. So this will be now the integral r by k dagger be effective of r by k. So does this sound like anything familiar that we've seen before? Notice that this is just a simple matrix element between the basis states. So this is the way we write a one body interaction. Okay, so you see how the exercise I did. I turned this two body interaction here. We have two bodies because we have on both sides of the potential we have two wave functions, one representing one electron, one representing a hole in this case because we are summing over the states that are below the Fermi energy, and then we separate this integral here. And we call that this an effective potential, which only depends on a single label, okay, because we integrated over the other label. And then we're left with a single label here, okay? Single space label. Okay, so this is a one-body interaction now. So I reduced the one-body problem, the two-body problem, okay, to a one-body problem now, okay? One body interaction, one body problem. So this is essentially what the scenario we mentioned before, so one body problem. Okay, and notice that this is for example, in the context, which is where Hartree was working, in the context of atomic physics. Okay, because here we just have fixed a certain potential. We know that this may be the Coulomb interaction, but this Coulomb interaction could be acting on electron-electron interactions in an electron gas, okay? Or it could be the electron-electron interaction in atomic physics, right? So in atomic physics, we know that, so we have the nucleus here, and we have all the orbits. Let's draw them a la Bohr, okay? I know they're not like this, but just for the sake of the drawing, okay? And then we pick out a particular electron, okay? So we choose an electron here, and I know that this two-body interaction is, okay, we have all these electrons here going around their orbits, okay? But the Hartree approximation consists of separating one of these electrons, so we choose one, okay? Choose one electron. Okay, and what it says here that all the electrons below this electron, which are below the Fermi C, okay, we take as an effective potential. Okay. Okay, so this is what this means. So this effective potential is what you would obtain, for example, from Gauss law. This would be Gauss law. This is the potential of all, or due to all the electrons that are below the Fermi energy, because we know K is above the Fermi energy. So this is going to be the most external electron in this cloud, are the ones that are going to be outside the Fermi level, okay? The Fermi energy, oops. Okay, so we take the effective potential, which is what this integral here is doing. Okay, so that's what you do. That's what Hartree assumed that what's going to happen. So we calculate this effective potential. This just depends on the coordinate of the electron. So this would be the coordinate of the electron. So all these coordinates are R prime coordinates. These are R coordinates. Okay, so this would be just a one body. So these generate a field, okay, together with the nucleus, for example, and then we get this matrix element. Okay, so this is the Hartree average, the average that Hartree did for his problem. Okay, so now, for example, we could write the Schrödinger equation in the following way. Okay, we could go back to first quantization, so Schrödinger. Okay, and we could write it like this. We have a kinetic term plus my effective potential, R. You see that we got just a single label, which is the particle that's going around, okay? And we have here the free particle energies, and this is the new corrected energies here by K, okay? And then we can write this integrate, we'll multiply both sides by phi of K, okay? So on this side, we multiply by phi of K, R, and conjugate, okay? On both sides, and integrate, okay? And integrate, and we get this form here. So phi of K, R, okay? So we have the first term, the kinetic term. Okay, both are k's plus, then we have the term we had before with the effective potential. Okay, plus equals to e sub k. This doesn't involve any coordinates, so we can take it out of the integral, and we get p of k r dagger I of k. dr. Okay, so this is just one. This is the orthogonality relation, orthonormality relation. And we get, in effect, that E sub k prime. So this is essentially what we did with the diagrammatics. We get this, the excitation value here is just h k squared, because these are eigenfunctions of the momentum operator, okay? So we get just this plus the correction due to the Hartree approximation.
Teacher, can you put one moment the previous word? 1 second. To see something I missed.
Yes?
Yeah. Yeah, okay. That's fine.
Okay.
Thank you.
Okay.
Yeah, thank you.
Okay, so this is another way. This is sort of the first quantize. Okay, it's the differential approach. Okay, so the first quantize approach. You would do it like this, and so you get this. This is exactly what Hartree did, of course. When he did this, this was a long time. This was in the 40s, so all these developments hadn't taken place. Okay, so you just did it directly from the Schrödinger equation. So it's a very natural. So again, this is a way to corroborate that our diagrammatic approach is working fine. Okay, these quasi-particles that we obtain in this approximation are quasi-particles are exact. Okay, in this Hartree approximation. Okay, so they have an infinite lifetime and they don't decay. Okay. So they would have this new energy that we see here. Okay, so is it clear? Any questions about this?
Yes, teacher. Can you repeat the part of the arrow in the first 5K?
Of
Please.
the arrow? What
Yes.
arrow?
Yes, you put an arrow. Yeah, in the first line.
Yes.
A little arrow in the first term. No, at the left, in the first line.
Ah, okay. So I multiplied. Okay, so this is multiply both sides. Okay, multiply on left. Okay, so I multiplied on the left by phi of k. So this is here, right? And here, right? And integrate. Multiply on left and integrate. Is it clear?
Okay, thank
So
you.
I multiply from this side, I multiply by phi of k star, and from this side, I multiply by phi of k star, and then I integrated both sides. Okay, so I separated the first term. Okay, let me put here. Okay, so this would be like this, and we get multiplying by phi of k star here just generates this term and integrate. Okay, so that's what I did. Is it clear?
Yes, thank you.
Perfect. Okay, so now Hartree-Fock. Okay, Hartree-Fock. There's a. Okay, so now remember that we introduced another diagram of the same order. Okay, so we had introduced another diagram of same order. As heart tree, or let me call it tadpole. Okay, this diagram was this the oyster. Okay, so we have the oyster. And the oyster, I'm missing an S here. Okay, this oyster was just the interaction line. Then I had, for example, one version of the oyster would be this. Then we had a line going back here, okay? And this has an internal momentum. So here I had K here, K omega, and we have another line going here, K omega, okay? So this was a tadpole. And we calculated also this diagram here. But let me make a clarification here so you can identify exactly how the oyster is built. Okay, so here we have. Okay, so this would be just the interaction line. Okay, so notice that incoming arrow. So we put here a K. Okay, this will be the incoming arrow. Then out from this same, remember that this is going to be R and R prime, okay, in the integral. So let me put the integral here, and we'll figure out what the correct indices are. Okay, and we have phi R prime V R minus R prime and conjugate phi of R phi of R. Okay, so this is the form. So you see that now these are the incoming, okay? In, and these are the outgoing, out. Okay, so now we have K. So K is going in. So we have on the arc side, okay, R prime. Okay, so this should be K. Okay, and what other vector is going in? So we go in, and then this in this thing, this from this same vertex, this line's going out. So this line is going up to here. So this is coming out from here, okay, and into here, okay, and this is going to be the line L, right? And then this is going out, okay, and this has to go out with the same K. Do you see? So now this L is coming out from the R side. So from the R side coming out, so we need another in. So the other in is on the R prime. So this is going to be L, and this corresponds to L. Okay? And then the outs, okay? From the side of here, we get this out. Okay? And then this goes up, the second out is this K here on the R prime side. So this, okay? So what is this matrix element? LK, KL. Okay? Is it clear? How I now derive this for the tadpole. This was KL, KL, and now here it's LK, and then we switch KL. So this is why we call this the exchange interaction. Okay? Any questions there? Because this is really important to how to build all the diagrams. We're going to just see one slightly more complicated diagram, and we should know how to, and that's going to be second order. So we're going to have a slightly more complicated relationship between the indices in the polarization diagram. Okay. Okay, is this clear? So here you know how to connect the diagram, okay, and the integral, okay. Also, this diagram here, how to build the diagram. Goes in K, out goes L, okay. Goes into the R prime side, okay. Goes in, okay, and then K goes out like this. Okay. So that's how you build it, okay? So in the homework, I'm going to ask you some things about this diagram. For example, remember here, this diagram, okay? No fermion loop. Okay, so you know there's going to be a minus sign in difference with the tadpole, okay? So that's going to be an important detail for the problem I'm going to send you, okay? So if we take into account, okay, if we account for the oyster, then what do we have? Then we have the double propagator, okay? And I'm going to do it here quickly because we've done this exercise a few times. So here we have the tadpole, and then we have the oyster. Okay, and then we're going to have so these are the first order, okay, first order. And then we're going to have the different combinations. So we could have a double tadpole. Okay, and we can have a double oyster. Okay, and the double oyster I'm going to draw like this. Okay, and then we're going to have a cross term. This cross term is going to be, okay, either this order here, okay, or this order here. Okay, so you see that this is remember this is all again K omega space. Everything is algebraic. Okay, so we can, and you can go to high orders here. Okay, so you see that so we could group this and in the following way. So now we write it like this. Again, we extract a propagator outside, we get the first term, and then we get the combination of the tadpole and the, okay, and the oyster. Okay. And then you see that we get here, when we eliminate this propagator here, we get the, let me write it out at least once. So we get this guy. This is the square of the tadpole. And then we get twice the tadpole and the oyster. Okay, and then we get the square of the oyster. Okay. Okay, so this term plus higher order terms. So these three terms, this is the square of the tadpole plus twice the tadpole times the oyster plus the square of the oyster. Okay, so this is just this second term here is going to be the tadpole plus the oyster. Squared. Okay, so that's very, very easy to see. It's going to work. And then we can sum it up in the same way that we did before. And we get, as expected, we get, then this is 1 over 1 minus the tadpole propagator up, minus, okay, plus the oyster here. Okay, so now we add those two diagrams, okay, and the problem that I wanted to solve in the homework is that when we write, okay, so we apply here Feynman rules. Okay, and then we get 1. Okay, and once we simplify with the dividing by the propagator, we get omega minus e sub k plus I delta. Okay, minus, and we get again both. Okay, both of those loops. These have the associated the internal variable, which I call in common L. Okay, and we get then the tadpole contribution minus the I showed you this was L K K L. Okay, so this is the tadpole. That's the bare tadpole with the internal variable L, and this is just the factored out oyster. I mean, this is the tadpole. Okay, so these have to be summed over because this is an internal variable. So this is summed over below the Fermi energy. These both are holes, okay, below the Fermi energy, and we get this is the Hartree-Fock. So this is a contribution. The oyster is a contribution missed by Hartree, and then this is why Fock came into the picture here. You notice that the exchange integral was not in the Hartree approximation. Okay, so he was not describing fermions properly. Okay, Hartree did not describe fermions properly. Okay, because of this exchange effect. And Fock corrected this, and then we obtained this approximation. Okay, so this is a full Hartree-Fock. This is a very a very well-used first approximation to either the atomic the atomic problem or the electron gas. For example, in the electron gas, as we will see, I'll make an argument for you. We see that the tadpole contribution, if we take into account the positive background charge, the tadpole goes away, and the only contribution that we obtain is from the exchange contribution. Okay, but in the atomic contribution, you get both. In the atomic problem, you get both. Okay, so atomic. Let me just write that down. Okay, in atomic problem. Okay, you get both Hartree and Fock, while in the electron gas with a background positive charge. Okay, this is just a comment. You get only the Fock or exchange contribution. Okay, is it clear? Any questions?
Yes, Mr.
Yes.
In the last slide,
Yes.
The element matrix KLKL
Yes.
is represented by the tadpole.
Yes.
Yeah, that exists. But what happened with the propagator?
What propagator? You mean this one here?
No. It just in the same slide, but up in the before the apply the Feynman rules.
Yes, we applied the Feynman rules. Yes. So
Yeah.
you mean
that
this?
propagator. Yeah.
Yeah. So remember that this propagator here we divide. So this one disappears, and we get this.
Yeah,
Okay.
I don't see that propagator. Sorry.
Right. Yeah. So this is to the -1, right? So
Yeah.
this here is to the -1. So we're divided by this propagator here. Maybe it's not.
Yeah, I don't see that propagator. Sorry.
Let me make it more visible. Okay, so we get equal, then we have the propagator here multiplying by that. Okay? Okay, good. Okay, so I made the appropriate observations for you to address the problem in the second problem set. There's one observation I wanted to make here. Yes. Look at this term here. You see that the factor of 2, remember that the interaction, let me see where we have that explicitly. Aha, so you see here, in the Hartree result, I have minus I BKLKL, and there's a half here, okay? This is something that I didn't mention. Okay, so let me put here the factor of 2. So okay, so this is another observation I'm going to make. So in order to eliminate the factor of 2, and I want you to sit down and try to work this out. So, okay, factor of 2 in Okay, remember that this interaction line, you have minus I V K L M N over 2. Okay, so we were doing a summation over spin. So remember that over spin, okay? Over spin. Okay, so this is just, I mean, none of our interactions depend on spin, so always the sum over spin introduces a factor of 2. So when I say that you have to sum over the internal indices, so we have this sum here, okay? But we also have to sum over the spins of that electron. So we have, so really, so in the previous expressions, substitute this sum by this, okay? And this will give you just a factor of 2. Is that clear? And this 2 will cancel this factor of 2 here. And that's why we obtain, instead of VKLKL over 2, we obtain just VKLKL and VLKTL. Is that clear? That's all there is to it, okay? This, when we have spin dependencies in these interactions, okay, then this is another story. The summation here, you have to do it more carefully because there will be dependencies in the potential on the spin. But here there's no dependence on the spin. We don't care. So the same integral for both spin values. So we just multiply by 2. Okay, so is this all clear? I mean, we've been doing these sums for quite a while now, applying the Feynman rules, and we obtain the Green's functions, and from the Green's functions, we read off the new energies, okay? But notice here that we have not been able to calculate any integrals. We have not specified what problem we're doing, okay? We have not specified our problem until we write what V of R minus R prime is, okay? So in principle, that potential, okay, in principle, Coulomb, okay? What I'm going to show you now is that if we start with the bare Coulomb interaction, we run into big problems, okay? These big problems are associated with some integrals are going to diverge, and we're going to obtain nonsensical results, okay? So what we're going to do, the first exercise we're going to do is to sort of tell you about the end of the story, okay? Some other contributions that have to be added to the Hartree-Fock approximation in order for it to make complete sense, okay? And that's why you only do a Hartree-Fock is a very rough approximation, and generally you have to go to what is called the random phase approximation, which is a sort of the minimal approximation that is good for a system where we have electron-electron interactions, okay? So we start with the end of the story.
Teacher,
Yes.
I have a question. I
Yes.
have a question in the last step of in the previous one.
Previous one.
Yeah, in this case.
Yes.
At the final, why are you putting a minus in the second potential?
Here?
Yeah.
Okay, so that's a problem in the problem set. But remember, the source of this difference in sign comes from the fact that this guy has a fermion loop. Okay, and here, no fermion loop. Okay? So that's the source of this minus sign. Okay?
Yeah, thank you.
Remember that here we had a minus sign associated with the 0 time propagator.
Yes.
So here we also have the 0 time propagator. So that gives us a minus sign. But then we have to add another minus sign because of the fermion loop. And here we don't have it. So this gives this minus sign difference. Okay? So
Yeah.
write down the full diagram, and you'll see when you have here 2 propagators here, or you just need the interaction with this propagator here. Write it out, and see that you will get this minus sign here. Okay, so this is that question of yours is in the homework 2. Okay.
Yeah. Okay.
Good. Okay, so we saw with the end of the story, what do I mean? That I'm going to avoid, okay, we avoid, okay, Coulomb problems. And how do we avoid them? We are going to introduce a new form for the potential. So this is the potential we need. Okay, and this potential, we're going to put some prefactor, which I'm going to tell you how it behaves. This is an A here, and then this is the Coulomb interaction. Okay, but then we're going to put a term here, an exponential, and this exponential is going to depend with the separation between the 2 particles, and it's going to have this scale, length scale. Okay, so this is the same A as I have in both places. Okay, so this is called the Yukawa potential. Okay, and it's a potential that works very well. This is invented for nuclear physics. Okay, originally. So what does this do? Well, the Coulomb potential, if you draw the Coulomb potential here, okay. So we have the Coulomb potential, okay, as a function of r minus r prime. Okay, so this is decay. This has a very long tail. Remember, this is a power law. This is just without the exponential. This will be a power law. Okay, while the Yukawa potential, okay, Yukawa is going to decay exponentially fast. Okay, exponential. Okay, so what if you've heard, for example, these things, problems with power laws, for example. When you try to integrate power laws, sometimes these tails, any integral that has a decay like 1 over r, and you integrate over volume, the tail makes the integral diverge. Okay, so what we're going to do is we're going to regularize. Okay, this is another regularization. We're going to introduce this the exponential decay, so that the exponential decay kills the tail. Okay, so this is going to decay much quicker. So when r is much closer to r prime, then this is essentially described by the Coulomb interaction. But when you go a long way from r prime, then this decays much faster in the exponential case. Okay, So this is used in nuclear physics because the forces are short-ranged. Okay, so we have a range. In nuclear physics, this will be the range of the interaction. In nuclear physics, range of interaction. Okay, in condensed matter physics, this is going to be, okay, in condensed matter physics, condensed matter physics, that is electron gases, for example, or atomic, or the atomic electrons in atoms problem. This will be the screening length. Screening length. Okay, and let me sort of go a little further to try to explain what this means physically. So imagine that you have a lattice, okay? And these are the positive nuclei, okay? And then you have the electrons, okay? And then you have the little electrons going around here. So let's suppose that we have an electron here like this, okay? So let's suppose we choose this electron as a center, and the Coulomb interaction makes this electron repel this electron, goes away. And this repels the electron, repels, okay? And what is going on is that then you're left with just the electron, this reference electron we chose here, and then we have the positive, okay? The positive nuclei, and the other electrons were sort of thrown out of a certain radius. Okay, so now the electrons are going to be here. So you see now that this electron here is going to be screened by all this positive charge. You see? So now the charge of the electron, when I go away, the electric field, okay, which is going like inside here, okay, all these electric fields going inside here. When I go outside here, it gets screened, okay, screening by positive charges. Okay, and these electrons are not going to see, actually, they're going to see a net positive charge inside this volume, and by Gauss' law, then these electrons, essentially this interaction, this Coulomb interaction is going to decay much more rapidly because of the screening, okay? And this is essentially the screening phenomenon, okay? Screening. Okay, so this is essentially what we're going to try to describe here. So if we use this potential, we're assuming that somehow this effect is happening, okay? But in the end, okay, in the end of the story, okay, here, let me just emphasize with another color. Here, A is a parameter. Okay, we put in by hand, okay, put in by hand. But as when the end of this section, we're going to derive it, okay? So in the end we will derive it using diagrammatics. Okay, so that's I sort of made the picture of the whole the rest of the classes that we're going to have. So here we assume first that we have this this string interaction, okay, and we don't know A, and then I'm going to tell you how we can, through diagrammatics, derive actually that this is happening, okay, and how, for example, Hartree-Fock fails completely when we don't take into account the screening length. Okay, is it clear? Let me tell you just 1 second how this formula. So we have that this formula here is now the Yukawa potential. So we have AB0 e to the minus r prime over A r minus r prime. Okay. This prefactor here is important because in order to obtain the Coulomb limit, okay, we need to take A to infinity. Okay, so what happens? A goes to infinity, this goes to 0, and this goes to 1. Okay, but then this goes to infinity here, so it doesn't make sense. So the other condition I'm going to impose is that d0 times A goes to E squared when A goes to infinity. Okay, so then when I take A to infinity, this goes to 1, and the other, and this, then A goes to infinity, we get E squared over r minus r prime. Okay, is that clear? So this is a limit we're going to apply. We're going to do all the calculations with this exponential term here, but then we're going to try to see what our results mean in this limit. Okay, so this will be a limit. Any questions there?
No.
Okay, okay, it's completely clear. So the other thing we're going to do, so this is one observation, is that, okay, summing things is not so easy. Doing discrete mathematics is always much more difficult than doing continuous mathematics. That's why Newton invented continuum mathematics, okay? So we're going to substitute, okay, summations over k, and this is what we do with the internal variables. We're going to go to an integral, okay? So we know this is a quasi-continuum, okay? So this is going to be integral over 2 pi, okay? And then, you know, this cannot be equal because this sum is dimensionless, and this has dimensions of 1 over L to the cube. So we have to multiply by a volume. Okay? So this is a substitution we're going to do. Okay? So this is generally behaves, this is a good approximation as long as you're treating, okay, for fermions. Fermions, it's fine because fermions don't suffer from this condensation phenomenon, okay? But for when you have bosons, you cannot do those. You cannot do this very close to t equals to 0. But generally, as this is a quasi-continuum of levels, quasi-continuum, okay, then it's a very good approximation that we substitute discrete mathematics. This is discrete with continuum mathematics, okay? So this correspondence you can use very well in fermion systems and boson systems for t different from 0. If you have no, okay? Good. Good. If you have no condensation. Okay, you know boson systems condensate. Okay, this is how you get superfluid helium, for example. You get these quantum liquids. This is due to condensation. And when condensation happens, this is a very bad approximation. Okay, but when you're above the condensation temperature, then it's good for both fermions and bosons. So this is generally an exchange we're going to do in order to be able to calculate. Okay, any questions? Okay, so let's at least begin doing the calculate the Hartree-Fock energies. Okay, so we have EK prime. Okay, Hartree-Fock energies. Okay, with Yukawa potential. Okay, let me draw this a little bit below here. Okay, so we get E sub k prime, okay, the perturbed energies. So we get the free particle energies, okay, plus omega, and when you're changing the sum, there's going to be an integral, and this is going to be an integral for L below kf, dk cubed. Okay, 2 pi cubed, and then we have v kl minus v l kkl. Okay, so that's the integral we have to do. So first we remember that these are going to be two integrals. I missed here, this is a mistake. So this has to be integral over L. Okay, all the L's below the Fermi energy. Okay, so the K is an external label here. These are external labels, and the L's are integrated over. So we have to start with the integrals inside. Okay, so let's calculate a generic integral. We'll calculate both integrals at the same time. So let's start with the VKLMN. Okay, and this is going to be a V0. Okay, this is due to the Yukawa potential. Then we have dr prime, and then we have phi k dagger r y k l r prime. Okay, and then we have the rest of the Yukawa potential. Okay, and then we have the other two wave functions, M, R, and N. So very good, okay? So recall that we chose the potential, the explicit form of the potential, and then we have here, okay, these are also going to be the free wave function. So this is going to be I minus, because of the conjugation, K dot R, okay, over square root of omega, okay. The square root of omega, you see here that already that we're going to preserve dimensions because each of these is going to generate a square root, okay? And the same for each one. So we have the same expression here with R prime, okay? Let me just write a second one, minus, and then we have L dot R prime, and then we have the square root of omega. Is that all the calculations we're doing in a certain volume, okay? So this is volume defined by this omega here. And the same for these two, okay? So now we are going to just write this really space so you know everything that we're doing here. So we have V0 over omega squared, okay? We're going to put this A below here, so we have symmetry in this expression for the Yukawa potential, and we're going to get dr prime, okay? And we are going to, all these exponentials are going to bring together, okay? We just skipped half a step, we get kr, okay, plus L dot R prime minus MR, okay, minus N dot R prime. Okay, these are all the exponentials, and then we get this times, okay, e to the minus R prime over A, and then we get R minus R prime over A. Okay, did I miss anything? Okay, I think not. Okay, so again, we're going to do a change of variables we did before. Remember, we did this some time ago. So we're going to call R minus R prime. We're going to call R floor, and then R plus R prime over 2. No, this here we don't need the over 2. We have, this is going to be bigger. Okay? So from here, you obtain, is just algebra, so we're just going to put, so we obtain that R is equal to R floor plus big R, okay, over 2. And R prime is going to be a big R minus R floor over 2. Okay, so with this substitution, we end up, just skip a step so you have something to think about. It's just, it's very easy to obtain. You get V0 over omega squared, and then we get the integral. Okay, so work out Jacobian. Okay, should be 1. And we get dr, and then we get the exponential of minus, okay, R over 2. And then we have K minus M plus L minus N. Okay, these are all wave vectors. Then you get R floor over A minus, and you get R floor here over A. Okay, and then we get e to the I R floor over 2, K minus L n minus n. Okay, so that's the full expression here. So the use of this coordinate transformation is that, again, as in the case we worked out before, we can now separate the R floor integral from the big R integral. So we can do the big R integral. So this integral here, okay, nothing here depends on big R, everything depends on small r. So this is just the delta function, okay, of k plus L, comma, n plus n. Okay. Notice also that this can be put as, this means that, okay, this means that k plus L is equal to n plus n. Okay. Okay, but this can also be written as k minus m is equal to n minus L. Okay, so you see that in this combination here, you get k minus n, this is k minus n, m, and is equal to n minus L. So this is just twice k minus n, 2 times k minus n. Okay, and this 2 with this 2 cancel. Okay, this is a very nice form after this transformation. So it was carefully concocted for this. So we get V0 and we get A over omega squared. Okay, and we just left with the integral over R floor, e to the minus R over A, okay, R floor over A. So you notice I multiplied and divided by A here, and we get e to the minus R floor over 2, okay, 2 times k minus n. Okay, that will just. And finally, we have the delta k plus L is n plus n. Okay, any questions here? Okay, so you have to work out this small exercise here to go from substituting. Okay, so you have to substitute now the change of variables every time we have R and R prime. We substitute, okay, by this combination here, and then see what labels are left in both exponentials and verify. Okay, so verify this. Okay, and we get this integral here. This is an emblematic integral. It's a one of, yeah, I mean, as common as the Coulomb interaction. Okay, so now you do that integral. That's an integral with pure exponentials. Okay, you can use Mathematica. You can use either integrate by yourself. But this is a three-dimensional integral. Okay, so you have to do the angular integral and all this, but I mean it's straightforward. And you should get this 4 pi. Okay, if you have any difficulties with the integral, just we can discuss this in a class. Okay, just to review what you've seen before. Okay, so this is the result. So this is the VKLMN. Okay, you get 1 over omega. You get 1 plus k minus m squared. Okay, and I missed something here. Remember that this cannot just be the delta function. This has to be a delta function with an omega, because it has dimensions of is remember I always put just this is a three-dimensional integral. Okay, so you get that omega there, and this is why you only get just a single factor of omega here. Okay, and this is the general solution. Okay, k squared. Let me see if I can make the mistakes. Okay. So we just have to make the limits the correct limit. So we have now the limit of KL, okay? So notice that this is KLMN here. So if we have this combination, so K is going to be equal to M, you see? These two are the same. So KK and L is equal to N, okay? So K is equal to M makes this for a very simple limit. So we have B0 A cubed, okay? Delta A plus L, N plus N over omega times 1. Okay? So this will be the tadpole. Well, not the full tadpole because yeah, it's a tadpole. Here, and this is the already summed. We haven't summed, okay, for a particular L, for a particular L. We have to now sum over L's, and then we have the integral we haven't done yet, okay, the integral over the L's, okay. So we have this will be the tadpole term, and then we have the other guy, the LKKL term is going to be just what we have there, okay? This one here. So in this case, we have BKLMN, okay? So L is different from K, so this is not equal to this guy, okay? So we have just the previous integral there. Let me put it like this. A cubed 1 over omega, and then 1 plus K minus M squared okay, K plus L M plus L. Okay, so this is the oyster factor. Okay, any questions here? Okay, so when we see a next class, we're going to calculate this this expression here. So we have EK. This is what we are going to obtain. So we have 1 over omega. The first term is going to be the first term is going to be very easy. The tadpole term is going to be very easy to integrate. It's just going to be the volume times the prefactor. Okay, so we're going to get this V0 times a to the 5. Okay, kf to the 5 over 5 pi. Okay, and then we're going to get we're going to join together all the k squared dependencies. So we're going to have the free term, okay, and this is the bare mass of the electron, plus 2b a to the 5, okay, kf cubed h squared. Okay, and this is going to be multiplied by k squared. Okay, so you see here the quadratic approximation, then we have this energy shift here. This is the energy shift. Okay, and this is the corrections, another correction to another addition. Okay, so this is the free particle k-squared term, and then you get another correction to the k-squared term from here. Okay, but notice that we can map this onto h squared k squared over 2m. Okay, so this is just coming from here. Okay, because this is just a shift in energy, it doesn't matter. We just shift the parabola. Okay, this is a shifted parabola, and then we can write 1 over m. Effective mass is going to be 1 over m, just the free term coming from here, and then we're going to have 4 v0 a to the 5 kx cubed over 3 pi. Okay, and finally, this implies that our new effective mass, okay, is going to be the old effective mass over the effect of this. Okay, so you see, as long, this is a very interesting result, as long as we have a finite screening length, so this is, let me write this a little better here so you don't confuse this with a 9. A to the 5, okay? So as long as A is finite, okay? A finite, this result makes sense, and this we get a new, okay, quasi-particle mass. Okay, and this all works fine. If, well, on the other hand, okay, we have that V0 times A goes to E squared when A goes to infinity, but what happens with this guy? This goes to infinity. So when we try to take the Coulomb limit, this is going to go like E squared times A to the 4th. So this is blowing up. So this blows up and the effective mass is 0. So this doesn't make sense, okay? Does not make sense, does not make sense for Coulomb case. This is the divergence I was talking to you about. The Hartree-Fock approximation does not make sense if we don't have screening. So screening has to come from someplace. Here we put it in by hand with this parameter A. But if this parameter A is taken to infinity, then all this calculation blows up and it doesn't work. Okay? So in the next class, our next class, we're going to see how we fix this problem, taking into account other diagrams that become important, namely the polarization diagrams, and we're going to see the contribution from those diagrams and how we can obtain the dielectric constant of an interacting electron gas. Okay? So let's stop here, and if you have any questions. No question?
Professor, with the Hartree approximation, we use the Hartree approximation to transform to a problem of two bodies to a problem of one body, right?
Right.
So we can use to make a problem of three bodies and reduce to a one body problem or not?
No, no. The thing is that this is something that is associated with the structure of this interval here. Remember, so the three-body problem, we would have to see what this is here. So in a three-body problem, you would have an extra phi function here. So that would be a function of three labels. Okay. So you would have to devise, and this is actually something you do with the with other approximations. I don't recall their names, but when you have two labels, you can also do what is called a mean field approximation. Okay, and you can do sort of a Hartree-Fock. Remember that here you can also incorporate the Fock term. You would have just two contributions to effective interaction. One where you have R prime and R prime in both sides, and the other one where you have R prime and R in this case. Okay, so when you have the three-body interaction, it's more complicated, but there are ways to do what is called a mean field approximation, which is a little more sophisticated than this Hartree approach, and you can reduce higher order interactions to lower order interactions. Okay, but generally you won't do that. I mean, if you have three-body interactions, you generally approach the problem from a very different point of view. Okay, you won't do this kind of approach when you have a three-body problem. And as I reminded you, everything until we know in nature, everything is a two-body interactions, even in high energy physics. So you take into account a high density, for example, high density problems in a completely different way from this one. Okay, so don't try to go beyond the two-body interaction with this approach. Okay. Any other question? No? Yes? Okay, so let's stop here. If you're going to go to this seminar we have at 6, so that you can, I'm going to attend to this seminar because there's lots of, supposedly the person who's making the seminar is an expert on internet classes, so webinars and this kind of thing. So hopefully I'll learn something from that. Okay, remember to tell me anything about the style of the class also. Okay, please, if you have some observations where we can improve. Okay, maybe my choice of colors, I think it's rather erratic, but if you have any observations, please tell me, write to me, and we'll try to make adjustments, okay? Okay, so let's stop here. Okay, so see you tomorrow.
See you.
See you, Mr. Bye.